Let me take another example of this idea, solving for a function where I only know the derivative or the derivatives of the function that I want. So here, let's say that I've got a watermelon and I've got a slow motion camera pointed at this watermelon. And what I'm going to do is I'm going to explode this watermelon and put the video up on YouTube. So what happens? Let me be more specific. I would like to find out how high up, say, some chunk of this watermelon is going to go before it starts to fall back down to the earth. Now, I could figure that out if I had a function which told me at time t, how high up is the chunk of exploded watermelon. So here they go, hither and yon. My ultimate goal is to know what the maximum height was. But on the way there, I want a function, again, I'm going to call this h of t, that describes the height of a chunk of watermelon, t seconds after detonation. I don't know what this function is going to be just yet, but I know things about what the derivative of such a function should be like. Again, I am doing this on Earth. So I know that the second derivative of my function should be negative 9.8 meters per second squared. Maybe someday I'll be able to get enough dollars off YouTube and do this on the moon. But for right now, I am working under Earth gravity. And actually, it's important that I use a slow motion camera here, because I was able to look at that piece of watermelon in my footage and determine its initial velocity, right? I need that extra piece of information in order to solve this antiderivative problem. So my h prime at time 0, what is the initial velocity for this chunk? For here, I've got 15 meters per second. Now, what I'm going to do is the same process as in my previous video. I'm going to calculate what could my antiderivative be. If my second derivative is a constant, my first derivative must be negative 9.8 times t plus some other constant that I need to solve for. The only kind of function that can have negative 9.8 as its derivative is a function that has negative 9.8 times my variable t plus a constant. How do I solve for that constant? I already know at time 0, my initial velocity is supposed to be 15 meters per second. So if t equals 0 and velocity equals 15, then my constant has to be equal to 15. Now I'll do one more antiderivative. What function or what functions can have a derivative, again, this is going to be the h prime of a function I just figured out, negative 9.8 t plus 15. Well, the only function that can have that as a derivative, using my antiderivative rules, I'm going to have a quadratic term. This will be negative 9.8 divided by 2 times t squared. I'm not done yet. I'm just stopping here to fill in the fraction. So there's my antiderivative of negative 9.8t. I need to add to this plus 15t, and there will be some constant plus c. Okay. I need to solve for this new constant here, even though I use the same letter. It's a different constant than before, right? These are potentially different numbers. Now, what I'm going to do is I'm going to say, where was this chunk of watermelon at time 0? If I reverse the footage, my watermelon reassembles itself. And where did it start? It was on the ground. How high are you when you're on the ground? You are height 0 meters. So h of 0 is going to be 0. And just like before, h of 0 is supposed to be equal to, all right, I've got a fraction times 0 squared. That's just 0. I've got 15 times 0. That's just 0. And I've got a constant. So my unknown constant must be 0. Okay, so now I've got the function that I wanted. The function which predicts the height of the watermelon, t seconds after detonation, has this formula. So now I can start to make predictions. The function that I care about is negative 9.8 t squared, all divided by 2, plus 15t. This is a little, I'm trying to get rid of these pictures. I do not need them anymore. Okay, again, the thing that I want here is the maximum height. How do I find a maximum? Oh, yes, I know how to find a maximum. Critical values, first derivative test, second derivative test. I know how to do this. So what I'm going to do is I need the derivative of this function so I can identify its critical values. Do I have to calculate a derivative of this function? I already know the derivative of this function. So this was my h of t. Typo there. That was my h of t function. What is my h prime of t? That's negative 9.8 times t plus 15. That's it. Where can the derivative be equal to 0? I'm just going to solve this equation for t, right? 0 equals negative 9.8 times t plus 15. So it must be that t is then equal to 15 divided by 9.8. That is the only number t that will make this equal to 0. And I'll have just a single critical value. Is this critical value a maximum, a minimum? Neither. I'll use my second derivative test. Why do I use my second derivative test? Because I already know my second derivative. It's right here. The second derivative of this function is a negative number. It's a constant function. That means that my function is concave down. In fact, I know that this function is a parabola that's facing down. So it's going to have a single local maximum at exactly time equals 15 divided by 9.8. So knowing a little bit about gravity and knowing the initial velocity, the initial position of my departed watermelon, I can predict how high off the ground that piece of my watermelon got before it started falling again. Now, one thing I want to point out here is that the numbers in this formula are not an accident. So, anytime I have one of these physics type questions, if I say I have initial velocity, and I'll need some variable for that, let's call that v, and I have some initial height, let's call that, well, I'm already using h, let's use p for initial height. And I know that my acceleration is going to be on Earth about negative 9.8 meters per second squared. Let's get some units on these other quantities. Well, I know that my second derivative is just going to be negative 9.8. I know that my first derivative is going to be negative 9.8 times t. And what constant do I put here to make this equation match my initial velocity? Initial velocity is supposed to be h prime evaluated at 0. Well, the only constant that will work here is the same v constant, the initial velocity. I'll take my antiderivative again. Now I'll have negative 9.8t squared, all divided by 2. And then I'm going to add on v times t, and I'll have some constant again. And again, these are potentially different constants, this one here and this one here. Just, I'd run out of the alphabet eventually if I kept using different letters. What number do I put in here? Well, my h of 0 is supposed to be whatever number p is. If I put t equals 0 in here, the only way that works out is if this is exactly negative 9.8 t squared, all divided by 2. There's that. And I need to add to this plus vt plus my initial position p. So this function, this predictive tool to know where an object will fly after I eject it from the surface of the Earth, the coefficients of this function are completely determined by the parameters I'm told at the beginning of this problem. And in fact, if I had different acceleration here, then I just have a different number here for my second derivative, and I'd have a different number for my coefficient on the t squared term. So I can make these predictions based off of my initial measurements. I can set up this physical situation. I can measure some of these quantities to begin with, and I can build a model which predicts things about the watermelon that I did not directly measure.